Laurent Gatto, MSnbase efficient and elegant R-based processing of raw mass spectrometry data. 444. Today I'll be presenting how the latest version of the MSnbase package can be used to efficiently handle raw mass spectrometry data. So let me start by providing a little bit of background about the software. MSnbase is an R and bioconductor package that has been publicly available since October 2010. It is developed and maintained by a core group of developers, myself, Sebastian, Gabe, and Johannes Reiner, and has also benefited from numerous external contributions. The package is thoroughly tested and documented, and you'll be able to find much more information on the MSnbase webpage. MSnbase offers a wide range of functionality, but today I'll be focusing on the efficient handling of raw mass spectrometry data. More details about this specific feature can be found in the recent MSnbase preprint. But let me start by clarifying what we mean by raw data. Mass spectrometry data is composed by a collection of spectra, and each spectrum is annotated by a set of metadata, such as its MS level, retention time, and many more. In the remainder of the talk, I'll be referring to the raw data as these spectra, typically stored as a collection of matrices containing the M over Z and intensity values, and their annotation here as the metadata, typically stored as one large table. In the following code chunk, I start by loading the MSnbase package, here on the first line. The data is stored in one of the many community-maintained open formats, such as MZML. And here, I load a file from the MSdata data package that I'll be using as an example. The MSnbase read MSdata function here can be used to parse that raw data file and create an R representation thereof. This representation is called an MSnX object or an mass spectrometry experiment. In the example here, I read a single file, but the function can read and handle many files. So the two important lines here are those that are highlighted. And this function can be used in two ways. The first one here, with mode equals in memory. This first usage of the function loads all the memory, that is the raw data and the metadata, into memory. And this is referred as to the in-memory backend. In the second line, only the metadata is loaded into memory. The raw data is left on disk and will be accessed and loaded into memory only when absolutely necessary, such, for example, when the raw data needs to be plotted. And this is referred to as the on-disk backend. And the goal of this representation is to benchmark the in-memory and the on-disk backend. So let me show you results of this benchmark. In the following figures, the in-memory backend is always shown in red, while the on-disk backend is presented in blue. Figures A and B here respectively represent the reading time and the final object size in memory. As expected, only reading and storing the metadata is significantly more efficient, as illustrated by reduced reading times and a reduced memory footprint of the on-disk backend. Figure C here on the top right illustrates the execution speed of a short filtering script that is shown on this slide. In this short script, we first filter all MS2 spectra and keep only those that have been acquired between 1000 and 3000 seconds, and then select the M over Z region, a slice of M over Z values between 120 and 135 daltons. And finally, we only keep 50% of the most intense spectra, that is, those that have a precursor intensity greater than 11 million. We can see here on figure 6 that thanks to an optimized lazy processing implementation, we see that the on-disk backend is more than 2 orders of magnitude faster than the in-memory backend. And finally, here at the bottom, we compare the time needed to actually access raw data in memory for the in-memory backend, shown here, or on disk for the on-disk backend, shown here on the right-hand side. And as expected, of course, accessing data on disk is slower. We can, however, see here on the left that the time needed to access data depends on how much of this raw data needs to be accessed. And this variability is can be seen very well for the in-memory backend. If we want to access all the data, and here all the data are 6,103 spectra of this test data, the in-memory backend is most efficient. However, when only subsets of data need to be accessed, then the reading time, or the reading in-memory time, becomes larger. And this is especially true when we need to access nearly all the data that is already in memory. And we can see here that the difference between the in-memory and the on-disk access becomes much smaller, especially when most of the data needs to be accessed. In conclusion, we have shown that the on-disk backend that is available since MSnbase version 2.0 is superior in most situations. It is faster and uses less memory. It's much more efficient when it comes to data manipulation. And it comes at a very reasonable cost when it comes to accessing raw data.